Hello everyone, my name is Yashvi Jetani along with my partner Purva Dethaliya. Today we are going to present on topic instruction format and addressing mode. The central processing unit is the brain of every computer executing instruction to perform a task. Understanding how this instruction work is the fundamental to computer architecture. The CPU executes instruction sequentially to carry out operation. Each instruction has a specific structure called its format. Each instruction defines a method to access data known as its addressing mode. The combination of format and addressing mode determines how efficiently the CPU processes information. This concept forms the foundation for understanding how computers execute programs at the hardware level. What is an instruction? An instruction is a command given to the CPU to perform a specific operation. It tells a processor exactly what action to take, such as editing number, moving data, or comparing values. Instructions are stored in a memory as a binary data sequence of 0 and 1s that the CPU can interrupt and execute. Each instruction is fetched, decoded, and then carried out by the processor. Example of instruction include add R1 R2 which add the content of two register and move A5 which moves the value 5 into register A. Instruction format overview opcode. The opcode fields specify the operation the CPU must perform, such as add, sub, store. This binary code tells the processor exactly what action to execute on the data. Operand. The operand field contains the data itself or the address where data is located. Instruction may have 0, 1, 2, 3 operands depending on the instruction format used by the architecture. Opcode and operand explain. Opcode specify the operation to perform. Example, add, subtraction, move data, tell CPU what action to execute. Operand specify data or location can be referred to register, memory address, immediate value. Example, add R1, R2. Type of instruction format. Zero address. Use an implicit stack of operands. Operation pops value, compute, and push result. Example, pop, push, and one address. Use a single accumulate register. Two address. Specify two operands explicitly. One operand is also destination. Example, add R1 R2 means R1 is equal to R1 plus R2. Three address. Specify two source and one destination. Example, add R1 R2 R3 means R1 is equal to R1 plus R2 plus R3. More operands increase flexibility but instruction size. Operand counts trade-offs. The number of operands in instruction format directly impact both capability and efficiency. Flexibility versus size trade-off. More operands allow complex operation in fewer instructions, but each additionally operand will increase the instruction size in a memory. Key consideration: zero address, smallest instruction but requires many stack operations. One address, complex to accumulate operation. Two operation, balance approach. One operand often server dual purpose. Three address, maximum flexibility, largest instruction size. Larger instruction means more memory bandwidth need and potentially slower instruction fetch cycle. Designer must balance visual power against memory efficiency and execution speed. Binary representation of instruction. Instructions are stored in a memory as a binary string. The CPU reads this bit and interrupts them to understand what operation to perform. A typically instruction might look like where the first bit represents the opcode and remaining bits specify the operands. The opcode bits tell the CPU which operation to execute, while operand bits identify register or memory address by decoding this binary pattern. The CPU transfers simple 1 and 0 into meaningful computational action that power all software operations. Addressing mode overview. Addressing mode defines how the CPU located operand data within an instruction. Different modes offer verified level of speed, flexibility, and memory access pattern. Immediate mode. Data in instruction. Direct mode. Address point to data. Indirect mode. Address point to the address. Register mode. Data in CPU register. Indexed mode. Base plus offset calculation. Immediate addressing mode. Data is embedded directly within the instruction itself. The operand value is a part of the instruction, not a reference to memory or register. Example, move A5. This instruction move the value 5 directly into the register A. The number 5 is immediate data contained in the instruction. Advantage: very fast execution. See, no additional memory access is required. The CPU has the data immediately available within the instruction. Direct addressing mode. Instruction contain the actual memory address of the operand. The CPU use this address to fetch data directly from that specified memory location. CPU fetch data directly from the specified memory location in a single memory access operation. This is a straightforward and commonly used. Example: load A1000. This instruction load the value stored at a memory address 1000 into register A. Indirect addressing mode. In indirect addressing, the instruction contains an address that points to another memory location holding the actual operand address. This required two memory access, first to fetch the pointer address, then the retrieve the actual data. Example: load A1000. The value at address 1000 contains the real address of the operand, while indirect addressing is slower due to the extra memory access. It provides greater flexibility. It enables dynamic memory access, support pointer-based data structure, and allow programmer to work with data whose location is determined at runtime. This mode is essential for implementing complex data structure and subroutine call. Register addressing mode. Operand is stored directly inside a CPU register. The CPU accesses data from its own internal register rather than external memory. Very fast access seen. No memory fetch is required. Register operation are the fastest addressing mode available to the CPU. Example: move A R1. The instruction move the value stored in a register R1 directly into the accumulator without accessing main memory. Index addressing mode. Effective address is equal to base address plus index address. The CPU calculates the final memory address by adding a base address to the value stored in an index register, enabling dynamic address computation. Commonly used for array and loop, index addressing is ideal for iterating through sequential data structure, as the index register can be incremented to access consecutive memory location. Example: load A1000 R. This instruction load data into register A from the memory address calculated as 1000 plus the current value in register R1, allowing flexible array implement access. Data flow in CPU. Fetch. The CPU retrieves the instruction from memory using the program counter. The instruction is loaded into the instruction register for decoding. The PC then increment to point to the next instruction in sequence. Execute. The CPU decodes the instruction, access required data from register or memory based on addressing mode. Perform the operation in ALU and store the result back to the destination register or memory location. Binary additional example in ALU. The arithmetic logic unit perform binary arithmetic operation. Here is a simple additional example. Register movement example. Data transfer between register and memory is fundamental to CPU operation. In this example, we move data from register R1 to a memory location using a store instruction. Example: store R1 2000. This copies the value in R1 to memory address 2000. The direction of data flow is crucial. Register to memory, store operation, memory to register, load operation. Arrows in a diagram indicate the direction of data movement during execution. Comparison of addressing modes. Speed. Immediately fast, direct, medium, indirect, slow, register faster, index medium. Usage: small constant data, simple memory access, flexible addressing, CPU register operation, array and loop handling. Advantage of instruction format and addressing modes. Efficient CPU operation. Well-designed instruction format enable the CPU to decode and execute instruction quickly, minimize processing overhead and maximize throughput. Faster instruction execution. Appropriate addressing mode reduce memory access time, allowing the CPU to retrieve operands more quickly and complete operation in fewer clock cycles. Flexible data access and better resource utilization. Multiple addressing models provide versatility while to access data, optimizing memory usage and enabling efficient handling of array pointers and complex data structures. Conclusion. Instruction format defines how instructions are structured in a memory, dividing to each instruction into opcode and operand fields. This standardized structure enables CPU to efficiently decode and execute commands from being the foundation of all computer operation. Addressing modes determine how the CPU located operand data, offering various methods from a fast register access to flexible indirect addressing. Together, instruction format and addressing modes are crucial from CPU performance, enabling efficient and execution flexibility data access. Thank you.
I am Purva Dethaliya. My ID number is 24CE028. Now I will demonstrate the concept of instruction format and addressing mode using an interactive web page, which helps to understanding how the CPU works in the visual way. Here we can see the basics concepts. First one is instruction set architecture. The complete vocabulary of binary operations a processor understand add, sub, MOV, JMP, and or. The ISA is the interface between software and hardware, defining every operations encoding. The second one is operation code, means opcode. The high order bits of an instruction that identify the which operation to perform. The CPU's decoder in read the opcode first, routing the instruction to the correct execution unit into the ALE or FP. The third one is operand field. The remaining bit specifies the data or its allocation, register number, memory address, or literal constants. The addressing mode determines how these bits are interpreted into the actual data. Then the instruction format. An instruction is divided into two parts, opcode and operand. Opcode tells what operations to perform and operand tells where the data it is. For example, add R1 and R2. Add is operand and add is opcode and R1 R2 are operands. This is also represented in binary form which CPU understands. This is the instruction execution life cycle. Then the addressing modes. An addressing modes defines how the CPU computes and the effective address of an operand. Each mode trades off speed, flexibility, and instruction size. The first one is immediate addressing. The operand values is embedded directly within the instruction word itself. The CPU needs zero additional memory access. The constant is the instruction field maximum speed, minimum speed, flex, used for some small constant of and loop bounds. This is an instruction and operands. The example is this. Then second one is direct addressing. The instruction contains the actual memory address and the operands. The CPU performs a memory access that access address, simple and predictable, but the address is hard code in the instructions, no runtime flexibility. Then the indirect addressing. The instruction contains a memory address that holds another address. The effective address to memory access required, read and pointer. Then the read data. Slow but powerful, enables dynamic pointer based access methods like linked list. Fourth one is register addressing. Both operands reside in CPU register, no memory access at all. Registers are on chip as RAM, accessible in a single cycle, the fastest possible operand access. RISC architect maximize register and addressing to reduce memory traffic. Then the fifth one is indexed addressing. Effective address is equal to base address plus index register. The instruction provides a base and the register holds an offset that can be incremented per iteration. The backbone of array traversal structure field access and loop-based memory patterns. Then the data flow animation. During data store instruction, the CPU drives data across the system bus into main memory. Data travels through the data bus and gets stored in memory. Then the binary simulations. The LLU performs arithmetic each clock cycle. Watch how to the 0101 add 0011 is resolved bit by bit with carry propagation animated in real time. This shows how data moves from register to memory. So through this web page, we can clearly understand how instructions are structured and how data is accessed by the CPUs. Visualization makes this concept easier to understand. Thank you.